Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is yet another video on graphing using calculus. If you have not seen my how-to video on all of this stuff right here, I highly recommend you view it. Otherwise, I'm just going to hop right into the example. In this problem, we're being asked to graph y equals the cube root of x squared minus 9. Very interesting function, actually. So let's go ahead and start with the simple stuff from good old elementary algebra, y-intercept. So if you let x equal 0, what happens? Well, you would get the cube root of negative 9, whatever that is. By the way, the cube root of a negative 9 is the negative cube root of 9, or negative 9 to the 1/3 if you want to write it that way. So there you go. Now that we have that, I'm going to go ahead and start building a table off to the right-hand side here, out of my habit here. Again, when x is 0, y is a negative 9 to the 1/3 power. I'll also go ahead and compute that very quickly, mainly because we're going to have to have some approximation to these values as we move forward. It's nice to know what they are. So this is roughly, I'll round to one decimal place, 2.1. All right, what else do we have? So after you find the y-intercept, x-intercepts are also nice to have. So you could see this function will turn into 0 at 3 and negative 3. No real math needed there. So I'll just state it here. X-intercepts are plus or minus 3, 0. And again, I'll state that over here in my table. So 3, 0, and negative 3, 0. There's no real order to what I'm writing there. I just write down as I come across stuff. Next thing I deal with, domain. It's kind of the next thing you learn in mathematics. The domain of that function is all real numbers, which is super nice because I know I don't have vertical asymptotes. But it's all real numbers because you could take the cube root of pretty much any, not just pretty much, you could take the cube root of anything. So there you go. You plug in anything you want. That's done. Let's see what else. Let's talk about symmetry. Symmetry of this. Symmetry can be very, very powerful. And in this case, if you take y of negative x, we would have the cubed root of a negative x being squared, and I forget the rest of it, minus 9. And of course, that is just a cubed root of x squared minus 9, which is y of x. So therefore, the function is even. Super nice to know. That means that we only have to graph the right-hand side super accurately, and then I'll just reflect it about the y-axis. Also, most of my questions from this point forward will just be focused on 0 to infinity, not negative infinity to infinity. Really nice to have that. All right. Let's see. We did our elementary algebra. We've done our intermediate algebra. We've done a little bit of high-level intermediate algebra, I guess, with the symmetry. Let's go ahead and figure out vertical asymptotes, which we just said a few moments ago are none, so we don't have to worry about those because there's no domain issue. But the horizontal asymptotes or oblique asymptotes, well, you know you would have a horizontal asymptote if the limit as x goes to positive or negative infinity becomes finite. You can easily see here as x goes to positive or negative infinity, this just becomes infinite. Also, you know you have an oblique asymptote if as x goes to positive or negative infinity, there is a term here that disappears. There is no term that disappears, so no dice. There's none of that stuff going on. So no horizontal asymptotes, no oblique asymptotes. We are pretty much done with the algebra. Now we step into calculus. And let's go ahead and take our first derivative, y prime. Well, I dislike radicals, so I'm going to rewrite this as x squared minus 9 to the 1/3 power. Taking the derivative of that, I will get 1/3 of that x squared minus 9. And that will be raised to the negative 2/3 power. And then by the chain rule, take the derivative of the interior, which is 2x. Cleaning this up, because it's nice to do, you will get 2x over 3 times x squared minus 9 raised to the 2/3 power. All of your prerequisite algebra is critical here. The simplifications, knowing that negative exponents moves things into denominators, all that stuff, because you need to know about domains of your derivative, what causes your derivative to become 0, all that fun stuff. We can easily see that y prime, and by the way, recall, this is an even function, so I'm only going to start this at 0. So I'll put 0 right here. Y prime becomes 0 at actually 0. So I'm going to put a dot there just to make myself know that y prime is 0 there. Also, y prime does not exist at positive 3. By the way, you might think, well, it also doesn't exist at negative 3. Yeah, I know that, but it's an even function. So I'm only really concerned about the positive side here. So positive 3, the derivative does not exist, which tells me because the function exists for all real numbers, but the derivative does not, either there's a kink or corner or cusp there, or a vertical asymptote. Okay, or I say vertical asymptote, what I mean is a vertical tangent line. I think I've said that a couple times now. So anyhow, let's go ahead and put some signs on this. What is y prime at a number between 0 and 3? Like 1. Y prime at 1 is positive because that numerator is positive and the denominator is being squared. So it's always positive. So I know that this is going to be positive. I should not use red ink for that. I'll use green. It's positive, so our function is increasing on that interval. If you try any number greater than 3, it will also be positive. So again, our function is increasing. And we do not see any local minimums or maximums. However, there is actually a local minimum, but we'll see that when we graph. Moving on, y double prime. Again, I'm only going to worry about the right side of the graph, and I guess I should probably take the derivative before I just willy-nilly start going and drawing a line. Let's take that derivative of that derivative, and this will be the quotient rule. Derivative of the numerator is 2 times the denominator minus the numerator times the derivative of the denominator, which would be actually 2 times x squared minus 9 to the negative 1/3 power, and then take the derivative by the chain rule of the interior argument, 2x. And let me just make sure that I didn't screw that up. So bring down 2/3, 3's and 3's cancel, 2x squared minus, yep. And now square that denominator, throw it downstairs. So 9 x squared minus 9 raised to the 4/3 power. That's squaring that denominator. Now I'm going to go ahead and multiply both numerator and denominator by an x squared minus 9 to the positive 1/3 power. That is, increase all those powers on x squared minus 9 by 1/3. So let's do it. We get 6 times, if you add 1/3 to that power, it's just a beautiful x squared minus 9 to the first. Minus, well, this is going to be 2 times 2 times 2, or 8x squared. Let me just double check that. Yep. And you add 1/3 to that power, it becomes the 0th power. So that's gone. Downstairs, we're adding 1/3 to its power as well. So let's go ahead and do that. X squared minus 9 to the 5/3. Final cleanup phase. 6x squared minus 8x squared is a negative 2x squared. Minus 54 all over 9 times x squared minus 9 to the 5/3. I've actually given this on an exam in the past. Let's see. All right. So the question is, when is y double prime 0 and when does y double prime not exist? Y double prime is actually equal to 0 when that negative 2x squared minus 54 is equal to 0. Well, if you really want to think about that, that won't happen because that's negative 2x squared is equal to positive 54, or in other words, x squared is equal to some negative number, right? There's no way for that to happen. A square will not become negative unless it's an imaginary number, but we're not allowing for that. So there's no way that y double prime is going to be 0. So all I worry about is the interval from 0 to infinity. And I know that y double prime just doesn't exist at 3. Technically negative 3 as well, but again, we're only dealing with the positive x values here because of symmetry. Pick any number between 0 and 3. Let's do 1. The numerator will be negative and the denominator will actually be negative. So it's concave up because negative over negative is positive. So our curve is concave up there. Now, if you plug in a number like greater than 3, like 20, something like that, again, the numerator is negative, but the denominator will be positive. So negative over positive is a negative, and we have concave down, and we now have everything we need. We actually didn't get any other points in this entire process. We did not get a single other point to plot or graph. That's okay. I'm going to go ahead and pause the video and draw down my axes. And you can see I've labeled them and everything. I didn't label my y-axis. Not that big of a deal, but you can see that I only for x values worried about 0, 1, 2, 3, mainly because we didn't have any other points to really worry about. Our function exists for all real numbers. So those red circles up here are where the derivative and the second derivative do not exist. Well, let's see what happens. All right, I know that according to my derivatives, y prime tells me, there's y prime, that my function is increasing on this interval and increasing on that interval. You can see that down to the left there. Also, we know we're concave up on the first interval and concave down on the second. So concave up and concave down. Let me plot 3, 0 and 0, negative 2.1. 3, 0 is right here. Oops, except I don't want to use that. I want to use blue ink here. So 3, 0 and 0, negative 2.1. And I'll try to use the same scale that I used for my x-axis. So this is roughly right here, 0, negative 2.1. All right, between 0, now I don't need this ruler anymore. Between 0 and x equals 3, it's increasing and concave up, and then it switches to be increasing and concave down. And remember, the derivative does not exist at 3. So it's going to look like this, increasing and concave up. Let me do this, left-handedness attacks again. By the way, 0 is going to be a local min. Even though we did not say that we had a local minimum, it was because we just didn't have a local minimum at any x value other than 0. You would not see using symmetry that you have a local minimum at 0. So that is kind of the weird thing about using symmetry, is that you don't get to see that local minimum until you graph it. But here we go. It's going to go vertical just briefly at x equals 3. That's where it switches concavity and it's still increasing. It does something like this. It's going to go off to infinity, but there you go. And now because it's even, I can graph the other side. My graph doesn't have to be super duper exact on the other side, although your instructor might require that. So maybe I should be as exact as possible. So 1, 2, 3, so that's negative 3 comma 0 right there. And we'll go ahead and try to mirror this image. Remember, it goes vertical right there. Just momentarily, so I'm going to try to showcase that. Notice I am taking a lot of care in this. And by the way, it's also concave down from this point forward. There we go. I know it's a little lopsided, but not too terrible. That is the graph of the cubed root of x squared minus 9. Very accurately done.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.